Hey 13 diplomas, welcome back. This is part B of your topic 7 recap. So here's an equilibrium reaction, okay, and this here is using concentrations of some of the species involved and a Kc value to calculate an unknown. So it says here, calculate the concentration of HI at equilibrium at 491 degrees if the concentration of H2 is this and the concentration of I2 is this, and we've got a Kc. So all you do is plug it in. So you do your Kc expression, products divided by reactants, rearrange to solve for HI. So it's going to be these two times up here and then the square root, and you end up with your answer. Okay, so that's quite nice and easy. So reaction quotient, what is this? So reaction quotient Q, this is before equilibrium is reached, okay? So before equilibrium is reached. And actually, these are some of the coolest questions because they can then ask you where would the equilibrium move to get to equilibrium. So we're still talking about this equilibrium here. Okay, so the Kc is 49.5 at 440. Okay, so in experiment 1, okay, experiment 1, they've given you, this is it here, the concentration. So they've given you H2, I2, and HI. So when you put it in to your Kc expression here, remember this is not at equilibrium, so we're just plugging in the values they've given us. We get a Kc of 4. Now 4 is way smaller than 49.5. So in order to reach equilibrium, we're going to have to make far more products so we get a bigger Kc. Because remember, Kc is products divided by reactants. Our Kc is too small. So to get a bigger Kc, we need far more products, which means our equilibrium needs to shift to the right. So that's quite a cool question that they can ask. If we look at experiment 2, here are the values. If we plug them in, we see that we get a Kc of 103. This is massive and way bigger than our Kc here, which means that in order to get to equilibrium and have a Kc of 49.5, our equilibrium needs to shift to the left, and we need to have more reactants to bring that value down. Hopefully that makes sense. Okay, and so if your Q equals your Kc, it's at equilibrium. If Q is greater than Kc, it always needs to shift to the left. And if Kc is greater than Q, it always needs to shift to the right. So here's a wee task just to check that you can do this. So feel free to pause the video and then watch the answer. So it says here the equilibrium constant for the reaction above is 1.7 at 500 K. Determine whether the reaction mixture is at equilibrium with these concentrations. So if it's not, explain where it needs to go. So if we plug all those into your Kc expression, so Kc is products divided by reactants, so NH3 divided by H2 cubed N2. So if you plug in all those values, you will end up with a value of 42.7. Now, our Kc that was given was 1.7 times 10 to the 2. This is bigger than the Kc we've got, which means that in order to get to our Kc, which is far bigger, our equilibrium needs to shift to the right and make more products. This is the style of question IB will ask you. So we can manipulate the Kc. These questions are not common, okay? And the two things that you can do is you can inverse the Kc or you can do multiples of the Kc. So inverse of the Kc just means you do 1 divided by the Kc, okay? And multiples is where you just double all of the exponents, okay? These questions are not common, so I'm just going to move on. Okay, Le Chatelier's principle. So Le Chatelier's principle, guys, is essentially any change that is made to the equilibrium is going to shift to minimize the change. I always tell kids when they're learning this stuff, whatever the change is, immediately say the direct opposite and then explain the change. It always makes things easier. Okay, so we're going to talk about what can be changed and how it can be changed. So as I've already said, it moves in a way to oppose the change. That's what the equilibrium does. That's what the principle states, okay? And your equilibrium will either move in the forwards or reverse direction to accommodate that change. Now, the three things that can affect your equilibrium are concentration, pressure, and temperature, and we're going to go through examples of those now. So concentration changes is the first one. So you can either increase the concentration of something, which is really, really easy. You just add more of something, okay? The harder one is decreasing the concentration of something. So you can't just like go in and pull out a few ions, right? In an aqueous solution, it doesn't work like that. So how on earth can you remove species from an equilibrium? What you need to realize is to remove a species, you have to do a side reaction. So another reaction that takes precedence, that removes it from our equilibrium and puts it into another reaction. Some good types of reaction are precipitates because they form a solid, and that removes those aqueous ions from the equilibrium. Now, you're not going to really be asked about this. It's just that you should actually understand that you can't just decrease the concentration of something. It just doesn't vanish to somewhere. So you have to do something to make that happen. And I'll go through how ammonia works because the Haber process is pretty important. Please note that concentration will not affect your Kc. Concentration will not affect your Kc. So here's an equilibrium we've seen before. Okay, let's talk about the fact that if I increase the concentration of Fe3+ by literally adding more. So how I get kids to answer this is that say the direct opposite first of all. So if the concentration of Fe3+ has been increased, then your equilibrium will shift to decrease the concentration of Fe3+ because it'll do the direct opposite. Okay, so EQ will shift to decrease the Fe3+. Now, if you look at your equilibrium, there's only one way that you can use up Fe3+. So if you move in the forwards direction, Fe3+ and SCN- are getting used to make the product. And if you go in the reverse direction, this is breaking up to make more. So if we're trying to decrease Fe3+, then our equilibrium has to be shifting to the right. And so that's what we're going to say next. So we're going to say that equilibrium will shift to decrease the Fe3+. It'll do this by favoring the forward or shift to the right. And that will mean that we end up with more of this being produced because we're shifting to the right, which will mean that the color will be more red. Hopefully that makes sense. Let's look at a different example. This example here is talking about removing. Now, this is the Haber process, probably one of the most important processes because it makes ammonia, which we use in multiple different, I suppose, parts of chemistry, manufacturing. One is to make your plant-based additives. Okay, so we add a lot of ammonia and fertilizers and things like that. So here we go. Here's ammonia, and they're saying we're going to remove ammonia. Now, the way this actually happens is that ammonia dissolves really nicely into water, and then that's how they actually remove it. So that's quite cool. So that's the way that that's getting removed. They're not going to ask you that in IB. You just need to explain it. So if this is getting the change is a decrease in concentration of NH3. So what's equilibrium going to do? Always state the direct opposite first. So the equilibrium is going to shift to increase the concentration of NH3. Okay, now how's it going to get more NH3? Well, if you look here in the forwards direction, that makes NH3, and the reverse direction breaks it up. So the equilibrium is going to shift to the right to make more, and that's exactly what happens. Okay, and that's as easy as it is to answer these questions. So you state the direct opposite and then which direction it's going to move. So because NH3 is being removed, the equilibrium is going to shift to increase the concentration of NH3, and to do this, the equilibrium will shift to the right. Hopefully that makes sense. Here's another example, and this one here's another removal one. So we can remove this here by forming a precipitate with barium. So if we ever wanted to remove some of these, we'd add some barium ions and it would form a precipitate. You wouldn't be expected to know that off by heart at all. It would simply say that this concentration was going down. What happens? So let's talk about what happens. So if the concentration of CrO4 2- goes down, what will happen is your equilibrium will shift to increase the concentration of CrO4 2-. Okay, how's it going to increase this concentration? Well, if you shift your equilibrium to the right, you make more of this, and if you shift to the left, you break it up. So we're going to shift to the right and make more. Hopefully that makes sense. So here's a really beautiful graph. I love these equilibrium graphs because you can see exactly what's going on. So when it's a horizontal line, as we've seen at the very start of these lessons, the horizontal line means equilibrium because the concentrations are not changing. Now, when you see a really sharp straight up or straight down, that means an increase, a concentration change up or down. So because H2 goes vertically up immediately, it means the concentration of H2 has been increased. And let's talk about what's happening here. Okay, so here you've got H2 increasing in concentration. What will the equilibrium do? The equilibrium is going to shift to decrease the concentration of H2. How will it decrease the concentration of H2? It'll do that by shifting, the equilibrium will shift to the right to make more products and use up the H2. So if the equilibrium shifts to the right, we would expect the concentration of NH3 to go up, which we see. And because N2's done nothing except get used up by the fact that the equilibrium's now shifting to the right, we would see the N2 decreasing, which we also see. And because this was increased, and because now we're shifting the equilibrium to the right in order to decrease this, we also see a decrease here. Hopefully that makes sense. So now let's talk about this change here where we see a sharp lowering of the concentration of NH3. This means NH3 has been removed, decrease in concentration. So if the concentration of NH3 has gone down, the equilibrium is going to shift to increase the concentration of NH3. And how will it do that? The NH3 will be increased by shifting the equilibrium to the right to make more, okay? And so if equilibrium shifting to the right, we'd expect NH3 to go up because that's what we're trying to increase, and the two reactant concentrations to go down, which we do see. And you can see here in this graph, the equilibrium is actually established at 3 different positions on this graph, and that's when those lines are horizontal, okay? Hopefully that makes sense. So which direction will the following move? So if you look here, what if O2 was increased? So if O2 is increased, the equilibrium will shift to decrease O2. And the only way to decrease O2 would be to move the equilibrium to the right. So equilibrium would move that way. What if H2 is decreased? If H2 is decreased, the equilibrium will shift to increase H2. The only way to make more H2 is to shift to the left. Hopefully you've understood that. I'm going to stop this video now so we can carry on with the rest of Le Chatelier's principle. See you soon.